in the packet. This is the title, Maximal Cohen-Macaulay Endomorphism Rings, N-Cluster Tilting, and Higher AR Theory. My mandate for this second talk was, so the first talk was supposed to be background and introduction to Cohen-Macaulay modules, and the second talk is supposed to be something deeply exciting that is happening currently in maximal Cohen-Macaulay representation theory. So we've already seen N-cluster tilting and higher AR theory in a couple of talks yesterday in what might be called a special case or an application. But I think that it's worth talking about the more general theory, mostly due to Osamu Uyama. So let me start with this first phrase. And point out a nuisance, a kind of annoyance that the endomorphism ring of a maximal Cohen-Macaulay module need not be, again, maximal Cohen-Macaulay. So one of the themes of my lecture yesterday was that maximal Cohen-Macaulay representation theory is very similar to representation theory of finite dimensional algebras. But this is something new. Of course, over a finite dimensional algebra, you take a finitely generated module, its endomorphism ring is again finitely generated. You don't leave your category. In general, though, this fails, and it would be nice for various applications if it were. So for example, yes. Yes, my ring is, I'm sorry, my ring is always commutative, local, and usually Cohen-Macaulay. But yes, of course, yes. But I guess this is the wrong word. I really mean the module that is the endomorphism ring. So I'm thinking, so the hums from M to M as a module over the base ring. It's a good point. So there's an ambiguity here. So I don't mean that the endomorphism ring is a Cohen-Macaulay ring. I mean that it's maximal Cohen-Macaulay over my original base ring. So let me give an example of one application in which this would be nice. And I won't say too much about this, but it's another topic of current research. A non-commutative Crepant resolution, often abbreviated NCCR, of a Gorenstein local domain is an algebra, let's call the domain R, is an algebra of the form endomorphisms of some ring or some module M, which with M a reflexive R module which has finite global dimension and is maximal Cohen-Macaulay as an R module. And one might, in the best of circumstances, one might like to take the module M to be maximal Cohen-Macaulay and then search for one of these algebras that's also maximal Cohen-Macaulay as an R module. And these are supposed to be some kind of algebraic analog or replacement of resolutions of singularities. But, as I say, this isn't automatic. This maximal Cohen-Macaulay condition is a real condition. So the most we can say in general is that the depth of sure I don't of a Hom is at least 2 if n has depth. At least 2. But the behavior is not predictable. So this is a standard application of what's called the depth lemma. Basically an application of the long exact sequence of Ext. But in general, depth can go up or down. And just to point out that this is a real problem, let me give you a couple of examples. Relatively elementary examples. Let's let R be a Cohen-Macaulay local normal domain of dimension D. At least 2 probably. And let's consider the maximal ideal. This has depth 1, always. But the endomorphism ring of the maximal ideal is just the ring you started with. So has maximal depth. So this is in some sense a good situation where the depth jumped by quite a lot. But yeah. Well, I think it's all true as I've got it. It's only interesting if D is at least 2. I'm sorry, I don't know who said that.
So D doesn't have to be at least 2?
Well, if D is 1, it's all true but boring.
No, but I mean n equal to R. Is that true?
But if it's a normal domain of dimension 1, then it's...
Oh, sorry, it's normal. Okay.
Yeah.
I missed that.
Right. The normality is what makes this true. So that's the depth jumping, which is great, but it can also go down. So for example, let's let R be power series in x squared, xy, y squared, yz, z squared, and xz. This is a three-dimensional normal domain, and let's let I be the ideal generated by all the terms involving x, all the monomials involving x. And let's let M be the first syzygy of I. Which is a module of rank 2. Then the endomorphism ring of M then M is Cohen-Macaulay, maximal Cohen-Macaulay, but its endomorphism ring has depth 2. Has to have depth at least 2 by the remark over there, but in this case it does drop. By the way, the reason I bring this example up is I mentioned yesterday that there are only 2 known examples of Cohen-Macaulay rings of dimension 3 or more with finite Cohen-Macaulay type that aren't hypersurfaces. And this is one of them. Whoops, of dimension. At least 3. So we find this bad behavior already in very nice examples. But maybe you object. It's not as nice as it could be. It's not Gorenstein, this ring. In fact, this was a question of Vasconcelos in the 80s sometime. No, 68, excuse me. If R is a Gorenstein ring and M is maximal Cohen-Macaulay, must its endomorphism ring be maximal Cohen-Macaulay? And it was open for quite some time, actually. The first counterexample was given by Jinnah in 78, I think. Based on a remark of Hochster. And just so you have one more example in your toolbox, let me show it to you. Let's take A to be the ring power series in x, y, z over some field and kill the Fermat cubic. Take B to be nothing but power series in 2 new variables. And R, the so-called Segre product. So this is the subring generated by XA, XB, YA, YB, ZA, and ZB inside A with these 2 new variables attached. Then the ideal, let's call it I, which is take the extension of the ideal generated by A in this bigger ring and intersect down to R. This is a counterexample. So Vasconcelos' question has a negative answer, but at least you had to work kind of hard to get one. I is the M, yes. Okay, thanks. It has depth 3, but endomorphism ring of depth 2. So now let's look for conditions on M, which we're going to assume is maximal Cohen-Macaulay, to force its endomorphism ring to be maximal Cohen-Macaulay. And recall that we decided in my lecture yesterday that Cohen-Macaulay representation theory works best over isolated singularities. So we may restrict to isolated singularities. Well, of course we may, but we're satisfied in doing so. If we can find good conditions, in this case, that will be progress. And so here's a lemma, which has been observed over and over. Let's let R be a Cohen-Macaulay local isolated singularity. Recall that this means it's not regular, but all of its localizations are away from the maximal ideal. And let's let M and N be two maximal Cohen-Macaulay R modules. Then the Hom, let's see, the depth of the Hom module from M to N is at least R, some integer R, if and only if X I from M to N is 0 for I going from 1 up to R minus 2. So this is a homological condition on the modules M and N, or on the single module M, that gives you good depth of the Hom. So in particular,
well, I guess you have to assume R is smaller or equal to D.
yes, thanks. Thanks. For R at most the dimension. So in particular, this endomorphism ring is maximal Cohen-Macaulay, has the largest possible depth, if and only if it has no self-extensions in the range 1 up to D minus 2. So this, whoops, where are we? In particular, this is no condition if D is at most 2, which explains why we have such greater success in these low dimensions than in higher dimensions. In the proof, I won't give the whole proof, but the proof is excuse me, the depth lemma for one direction plus the so-called acyclicity lemma for the other. So this motivates the following definition. Let M be a maximal Cohen-Macaulay R module. It's not particularly important what sort of ring R is at the moment, but in a moment it will be an isolated singularity. And let's fix some integer n. Then let's say M is n cluster tilting. And these next conditions will look familiar. So this add M, this is the all direct summands of direct sums of copies of M. The additive category generated by M. If that is equal to the set of maximal Cohen-Macaulay modules, so that x1 up to, make sure I get the indexing right, n minus 1 from x to m is 0. And symmetrically, such that x from m to x is also 0. These were introduced by Iyama. They were originally called maximally n orthogonal. It wasn't until later that the connection with cluster tilting came to light and the name was changed. So in particular, we should observe that if M is D minus 1 cluster tilting, where D is the dimension, then we have D minus 2 x vanishing, and so by the middle board, at least over an isolated singularity, we have the condition we've been looking for. So this is what justifies the expectation that these subcategories of the form add M for M and n cluster tilting module, are better behaved for doing representation theory. And as Osama pointed out yesterday, the case n equals 1 is no condition. On x, which means that 1 cluster tilting, so M is 1 cluster tilting, precisely if add M is the entire subcategory of maximal Cohen-Macaulay modules, i.e. R has finite Cohen-Macaulay type. And in this case, We'll continue up here. So still in the case n equals 1, the endomorphism ring of an additive generator for the whole maximal Cohen-Macaulay subcategory is called the Auslander algebra, or an Auslander algebra. For R. And we therefore call the endomorphism ring of an n cluster tilting module an n Auslander algebra. And as Osama said yesterday as well, the subcategory add M is an n cluster tilting subcategory. So we have found some modules, some maximal Cohen-Macaulay modules with good endomorphism rings. We hope to be able to do representation theory with them more easily. And here's the first major success. There is a higher Auslander-Ruyten theory for n cluster tilting categories due to EMI. So let me explain the main features of that. So let's call this a theorem. Let's assume that R is an isolated singularity. And M an n cluster tilting R module. And let's set curly C to be add M, the n cluster tilting subcategory. Then 3 statements, and I'll come back and explain each of them a bit more after I've gotten them all on the board. There is an equivalence denoted tau n, n is for n cluster tilting, from C modulo projectives to C modulo injective objects, injective in the subcategory, called higher AR translation, or translate. Second, there is functorial, excuse me, a functorial a functorial isomorphism Hom over R xy. This is stable Hom, modulo maps factoring through projectives with x to n, y and x in the other order, and applying the higher AR translation, and then take the dual. So this means matless dual. And third, I won't fit it in here.
X and Y are in C?
Oh, right, excuse me, thank you. For x and y in this cluster tilting subcategory. And third, for x in C, indecomposable, non-projective, there is an exact sequence, a unique exact sequence. Starting with the AR translate to y, make sure I get the indexing right, n minus 1, ending in x, where each y is in C, and maybe I'll give these maps names. If I try to pick names to match the standard ones, I'll miss, so I'll just call this F and this G. So F is almost, excuse me, it's right almost split. G is left almost split. And a minimality condition that I omit. So this, in a nutshell, is all of Auslander-Ruyton theory with ends decorating in various places. Very satisfactory generalization. So let me say a few things about who these characters are. It's not, there aren't any terribly significant new players from standard Auslander-Ruyton theory. They're just organized differently. So first of all, the tau n is nothing but tau n of x is nothing but, let's see, the dth syzygy, suddenly I'm switching to omegas for my syzygies, the transpose of the n minus first syzygy of x, and then dualize, where this now is Hom into the canonical module, which I guess I forgot to assume exists, but now it exists. And in the special case, remember that the most important case for us, the case that got us on this road, was the case where n is d minus 1. It's where the endomorphism ring is maximal Cohen-Macaulay. This tau n coincides with the so-called Nakayama functor, which is just matless dual, or excuse me, canonical dual followed by algebraic dual. usually denoted by nu. And I won't write this part down, but 3 comes from 2, exactly as in the classical case, that this exact sequence is nothing but the Sockle element on this side, which corresponds to the identity of this stable endomorphism ring on this side when x is equal to y. So when I started preparing this talk at home last week, I didn't know what was going to happen on Monday afternoon's talks. So I asked a question of the form, are there any examples? Presumably the videos will appear online at some point, and you can go back and check yesterday afternoon's talk and see that, yes, in fact, there are examples. So example 1 is, of course, these Geigel lensing either weighted projective lines or weighted projective spaces. See yesterday's talk by Osamu Uyama and mentioned in at least one other talk, as I recall. But let me give you a couple of others that haven't come up here so far, at least not that I've been paying attention. Let's consider the power series ring S in D variables, and let G be a finite subgroup of SLDK. Acting on S in the obvious way. And let's set R to be the invariant subring. So this is a d-dimensional complete Gorenstein normal domain. Gorenstein because I insisted that the subgroup be contained in SL rather than just in GL. And let's assume further that this invariant subring R has an isolated singularity, so it fits into the context we've been discussing, which in this case means no element of G except the identity has 1 for an eigenvalue. Then this is a result of Auslander, and I'm trying to sneak as much of the Mackay correspondence into these talks as I possibly can. The endomorphism ring of S as an R module. So S is a finitely generated R module and is in fact a maximal Cohen-Macaulay R module. This endomorphism ring is isomorphic to the twisted group ring of S and G. And in particular, is isomorphic to a direct sum of copies of S as R module, whence is maximal Cohen-Macaulay. So the additive subcategory of R modules generated by S is a D-1 cluster tilting subcategory. And therefore, one can do this higher Auslander-Reiten theory entirely within the additive subcategory generated by S. In the special case where D is 2, this is the so-called classical Mackay correspondence scenario. We get one cluster tilting hence R has finite Cohen-Macaulay type, as I already mentioned yesterday morning. This was the power series in two variables u and v invariance under a finite group. This was the result of Herzog and Auslander. Okay, I have time for one more example, and I have two in my notes. So let me skip to the last one. In the usual or classical Auslander-Reiten theory for two-dimensional Cohen-Macaulay rings, there is a player called the fundamental sequence. Which plays a central role. It's not accessible in any other dimension. If we denote by omega the canonical module, then it's characterized by xi from the residue field to omega being zero whenever I is different from 2, and when I is equal to 2, a single copy of the residue field. I guess K is the residue field. So what that means is there is a unique short exact sequence, unique up to isomorphism, of this form. This is an x1 of the maximal ideal by omega corresponding to the unique non-zero, unique up to scalars, non-zero element of x2, the residue field up to omega. And this is called the fundamental sequence. And what is its superpower? For any maximal Cohen-Macaulay module M, the Auslander-Righton sequence ending in M is, let me give the fundamental sequence a name. Let's call it phi for fundamental. Is nothing but Hom of M dual into the sequence phi. And I guess I should say non-projective here. And there's yet another theorem of Osamu that if R is a d-dimensional, and I didn't write down here isolated singularity. So I'm going to say isolated singularity just to be safe. It might not be. Essential. With a d minus 1 Custer tilting module, oops, this run-on sentence, then there is an n fundamental sequence playing the same role for higher Auslander-Righton sequences in the n-cluster tilting subcategory. So that's all I had to say for today. Thank you for listening.